Hello, everyone. I am delighted to share with you my research on the synthesis of antimicrobial biomaterials, and I would like to thank the organizing committee for the invitation to deliver this talk. I will quickly go through different points, starting from definitions of materials and required applications of antimicrobial biomaterials, and ending with a focus on my research in this regard. So, metal phosphates are purely inorganic materials composed of metal sides with phosphoric acid through the removal of 1, 2, or 3 hydrogen protons, but generally they are all collectively referred to as metal phosphates. So we have the metal phosphate with a phosphate group that have mainly nanofibrous morphology, and we have here 4 examples, and they will all be mentioned in our research in this presentation, I mean. So titanium phosphate, we have the P and Rho polymorphic forms, we have the zinc phosphate, and the strontium phosphate. With the metal hydrogen phosphate with 1 plugged side of the phosphate group, these structures are mainly nanolayered in their morphology and therefore have established applications based on their intercalation capacity and ion exchange properties. With metal dihydrogen phosphate, the literature reported random morphologies for this group of compounds, and thus high insolubility with applications in battery materials and other industrial applications. Regarding biomaterials, metal phosphates are mainly used in 4 major applications, namely dental cements, scaffolds, biocompatible coating, and anti-corrosive coating. Their choice was based on the composition of natural bone apatite and the presence of trace bifunctional elements and ions in the physiological system. However, nowadays we also know a number of additional bioinert metals, and there is a considerable progress in the synthesis of functional nanoparticles. Additionally, nowadays, metal phosphates in biomaterials applications are mainly calcium phosphate compounds with different resorbabilities. For instance, we have the hydroxyapatite and octacalcium phosphate that are quite stable and used in tissue engineering and scaffolds formation. And on the other side, we have the resorbable tricalcium phosphates and monocalcium phosphates that are used in bone and dental cements. Additionally, we have metal phosphates, and in this case are mainly calcium phosphate compounds as candidates in the formation of biocompatible coatings to metallic and polymeric substrates. The interest, particularly in calcium phosphate phases, lies in their capability of stimulating the osteoconduction and therefore osseointegration. However, we nowadays need more. We need means for decreasing the probability of inflammations and infections. For this, we need antimicrobials that can be antiviral, antibacterial, antifungal, and/or antiparasitic. These antimicrobials should be easily, safely, and cheaply synthesized agents that won't cause any adverse effects to their physiological contact site with a prolonged effectiveness. We have the metal nanoparticles as the growing antimicrobial agent, especially after the antibiotic resistance that has started to has started to be over any application for antibiotics, and we have 2 mechanisms for these antimicrobial metal nanoparticles. 2 mechanisms of action. The first is oxidative stress by generating free oxygen radicals, and the second is through non-oxidative mechanism with the release of metal ions that bind to the membrane and other cell components, leading to cell death. Now I'm going to summarize my attempts to functionalize different calcium phosphate compounds, and this work was already published in these three articles. First, using a bottom-up approach, I used an activated surface of titanium alloy, titanium aluminum vanadium alloy, and immersed it in 1.5 times concentrated solution of simulated body fluid. For you who don't know what is simulated body fluid, it is a solution with an ion concentration in pH very close to that of human blood plasma. This led to the heterogeneous nucleation and the crystallization of calcium-deficient carbonated apatite in 10 days treatment. Doping the immersion coating solution with strontium and zinc ions led to changes in carbonate content and coating uniformity. In both cases, strontium carbonate and zinc carbonate phases could be detected. Next, I accelerated the process by increasing the supersaturation of the simulated body fluid solution 10 times for calcium and phosphorus ions, and this resulted in the deposition of hydroxyapatite and octocalcium phosphate in 6 hours treatment. However, doping these highly supersaturated solutions with the strontium ions led to the deposition of brushite instead of hydroxyapatite. Doping with zinc also led to the deposition of brushite, which is monocalcium phosphate dihydrate calcium phosphate compound, but still hydroxyapatite could be detected at that time. I didn't have access to transmission electron microscopy, so I couldn't investigate at the nanoscale. But I started to think about the brushite phases, which were not really popular at that time. Everyone was thinking about the resorbable calcium phosphate phases as bad phases, but nowadays they are actually raising a lot of scientific research because of their capability in inducing more calcium phosphate deposition on the long term and therefore osseointegration. I mean bone formation. I decided afterwards to understand more about brushite, but I found that its anhydrous counterpart, which is known as the monatite, is more stable and would give a better understanding. So I used a two-step process to first synthesize monatite and then dope it with the ions of interest. And here I started to use silver, strontium, and zinc. At low doping ratio, low doping ratio, I mean the element of interest to the calcium, I got the doped monatites. They have the same morphological structure at the micro and nano scale of nanolayered phases. But at high doping ratios, I ended up with different phases in case of silver and zinc. With the strontium, monatite reserved its structure. This was confirmed using energy dispersive X-ray analysis in combination with scanning electron microscopy and scanning transmission electron microscopy. Since these minerals can easily encounter electron beam damage, I used the cryo high-resolution transmission electron microscopy, and I could confirm the crystallographic structure at the nanoscale of the monatite phases. And regarding the strontium-doped phases, I could find some expansion in their crystalline lattice, and this can be attributed to the substitution of the strontium ions in the places of calcium ions, since the strontium has an atomic radius bigger than calcium. The most interesting investigation nowadays is to determine the antimicrobial activity of synthesized phases. And for this, I used this standard protocol to determine the minimum inhibitory concentration, which is the minimum concentration required to have an inhibition in microbial growth, and the minimum bactericidal concentration, which is the minimum concentration needed to completely destroy any microbial growth. And in this graphical representation of the performed assay, you can see the gray dotted line in the middle of the graph. It represents the initial concentration of the colony forming units before the incubation, and the orange dotted line represents the colony forming unit concentration after 24 hours in the blank sample. We can see that only silver-doped monotype had the inhibitory and bactericidal effect, although the silver concentration in the silver-doped monotype is much lower than the zinc concentration in the zinc-doped monotype. We saw only insignificant decrease in the colony forming units in case of applying the zinc-doped monotype. At higher doping ratios, when we got the zinc phosphate and the silver phosphate, and the monotype doped with strontium at higher concentration, we started to see the minimum inhibitory concentration for the three of them. Strontium is the least effective in that regard, and of course silver continued to be the best. In order to know whether this antimicrobial activity has compromised the cytocompatibility, which is very important, because we cannot apply a material that is cytotoxic, I did a cell proliferation assay, from which we can see that silver is the most cytotoxic. And zinc is actually the least cytotoxic. This study showed us another functionality for strontium ions besides their stimulation of osseointegration, that at very high concentrations of strontium, they can actually start to show some antimicrobial activity, and that zinc is more effective antimicrobial agent than strontium, of course, but it is also more cytocompatible than silver. But at the end, silver is the most effective regarding its antimicrobial effect, and we can keep our investigation to low concentrations to avoid its cytotoxicity, and still it will be effective. Nowadays, silver nanoparticles are widely investigated and can be considered as a universal antimicrobial agent, but the actual antimicrobial effect comes from their release as ions. Now I'm going to share with you my investigations using silver as the antimicrobial agent and other metal phosphates than the calcium phosphate phases regularly used in these kind of applications. So I'm going to show you my investigations using titanium phosphate and zirconium phosphate in two different morphologies, the nanolayered and the nanofibrous morphologies, and we'll see the differences between them both. If you are also interested in having a good understanding of the whole subject, you can check our review articles that was published also very recently. The one at the very end of this slide. As you may recall, I showed you before the nanolayered zirconium and titanium phosphates and metal hydrogen phosphate compounds that have technological applications based on their intercalation capacity. In this study, I used a hydrothermal treatment to enrich their layered nanocrystals with intercalated silver ions and nanoparticles. As you can see, in this scanning electron microscopy analysis, Zirconium phosphate crystals are bigger in size, but they acquired almost half the amount of silver. These nanolayered crystals were studied with high-resolution transmission electron microscopy as well, and the size distribution analysis of nanoparticles showed their size homogeneity on both phases. For these two phases, I also studied the antimicrobial activity, and I did the cell proliferation assay, and they both showed good antimicrobial activity without much of compromise to their biocompatibility. So we can say that if we go back actually to this table, alpha titanium phosphate, when it is enriched with silver nanoparticles and silver ions, it has a better better cytocompatibility than zirconium phosphate. And also, the silver nanoparticles covered the surface of the nanolayered crystals, and more because they have a smaller size and they have incorporated more of the silver. It seems like the alpha titanium phosphate was successful to intercalate, to embed more silver ions compared to the alpha zirconium phosphate. So it seems like alpha titanium phosphate is a much better candidate, given that if it is encountered some very stressful physiological conditions when the pH will be very low, more of the silver ions will be released. So it will be actually more effective as an antimicrobial agent compared to the less intercalated silver ions in the alpha zirconium phosphate. There are actually a lot of investigations with zirconium phosphate, this alpha phase of zirconium phosphate, in bio-nanotechnology, but none actually was recorded for alpha titanium phosphate, and now we can see that it is even better. I did also another investigation on the other morphological and compositional form of titanium phosphate, the P and rho titanium phosphate. So I synthesized these two phases, which are actually polymorphic forms of each other. And using HRTM and STEM, scanning transmission electron microscopy, I could confirm their synthesis, and afterwards, using the hydrothermal treatment, their enrichment with the silver nanoparticles. Size distribution analysis showed the very similar sizes of the silver nanoparticles on both of the two polymorphs and those on the nanolayered zirconium and titanium phosphates. Here, there is no intercalation, and thus the silver ions release is much faster, and this might affect negatively their cytocompatibility. So there is an additional step needed to control the release of silver from these phases. As an application, I immersed these titanium alloy in phosphoric acid solutions, different concentrations, and performed the hydrothermal treatment. Titanium reacted with these solutions, resulting in a P titanium phosphate phases, as was confirmed by XRD analysis. The advantage of this method is the homogeneity of the resulted B titanium phosphate layer, regardless of the irregularities of the titanium alloy structure. And you can see here in this same image or images that I used a titanium alloy dental screw regularly used for these kind of applications. And you can see how it is completely covered with this layer regardless of the irregularities on the surface. And then in two-step process, I did the hydrothermal treatment to enrich the surface with the silver nanoparticles, and afterwards doped the resultant surfaces with strontium in an attempt to control silver release. And I did some ion release profile analysis. So I immersed the resultant coated surfaces in different solutions at neutral pH, which mimics the natural physiological condition, and in acidic pH to mimic the stressful physiological condition. And you can see here in this graph that doping, so the undoped are the upper panel, and the doped with the strontium ions are the lower panel. So you see these red points for strontium. You can easily see that without strontium doping, silver release is very fast. And if the release is very fast, we will get cellular damage very soon. But if it is slow and prolonged, we actually prolong the antimicrobial effectiveness and the success of this coat. We also try to visualize the cells of these bacteria, E. coli, and we found out that without any silver on the surface of the titanium alloy coated with p-titanium phosphate, we can still see the cells proliferate very well, but the three lower panels shows how this was completely reversed in the presence of silver and strontium. With this, I would like to conclude my talk. So metal phosphates can offer a great versatility regarding biomaterials applications, and the investigations should not only be limited to calcium phosphate phases in this regard. We now have seen some success with the magnesium phosphate and strontium phosphate and zinc phosphate. And with this research, I showed you other examples with titanium phosphate and zirconium phosphate. Regarding the antimicrobial agents, silver ions and silver nanoparticles can be considered as a universal antimicrobial agent. Of course, more research is taking place nowadays in my research group, where we are trying to scan for different bacterial and viruses. Zinc is also more compatible than silver, and it really deserves more scientific investigations in this regard. And the strontium was the, I would say, the surprise for me when I found out that strontium can actually show some antimicrobial effect beside its osseointegration effect. And also, when combining silver with strontium, we have seen that strontium controlled a little bit the release of silver ions and silver nanoparticles, and therefore decreased the cytotoxicity of silver-coated surfaces. And finally, we have also seen that the nano-layered zirconium phosphate and titanium phosphate show promising results as biocompatible and antimicrobial reservoirs. And the nanofibrous titanium phosphate phases present a new alternative and as an application for biocompatible coating of titanium alloys. Finally, I would like to thank all of these people that have contributed at different stages of me conducting this long-term research, and you for your attention, and I will be open for your questions. Thank you.